All right. Good morning, everyone. I think we'll get started. So I just want to remind you guys again, your homework night is due tomorrow night. Okay. So if you haven't finished your problems in this assignment, make sure you finish them by tomorrow night. And after you guys come back from the break on Wednesday, we'll have our exam number 3. Okay. All right, so let's get started with the lecture. First, we'll be reviewing what we learned last time. So last time we took a look on the definition of waves. So that's basically disturbance that propagates or moves from place it was created. So for example, if you create a water wave in the palm, it will propagate two-dimensionally. Okay. And then, for example, the gravitational waves, if two black hole merges, that will give out a gravitational wave that can be detected, and that's propagate in three-dimensional. All right. Um, so some basic quantities to describe waves. One is the wavelength. That basically that's the distance the wave travel if it goes from one peak to another peak. Okay, and then the time it takes is defined as period t. The frequency will be 1/t. All right, and then wave speed then will be equal to the distance travel of lambda divided by t, or equals to frequency times lambda. In this chapter or in this class, we'll be focusing on primarily on mechanical waves. So there are two types of mechanical waves. One is called transverse wave, and the other is called longitudinal wave. For a transverse wave, the media oscillate up and down while the wave propagate horizontally in that case. So basically, the displacement media, it has a direction that is perpendicular to the propagation of the wave. Okay, so those two are perpendicular to each other. For longitudinal waves, if wave goes in one direction, then the media will oscillate with its equilibrium position also in that direction, okay? But not going, it will go back and forth, but not moving with the wave, but they are displacement of media and the direction of the wave's propagation are in the same direction or same line of direction, okay? Um, when two waves they meet in space, they basically just add up algebraically. Okay, so if you have wave one, wave two, y1, y2, then you add y1, y2 up to get your resultant wave. Okay, wave can propagate also in two-dimensional. If you have two-dimensional wave, you can also add them up. So then in space, if you add different locations, so two waves may be traveling through different paths. So then because of that, they might interfere in, either constructively or destructively or in between. Okay. Um, so if you have two waves that come out of two sources, if the two sources are in phase, that means they give out identical waves in terms of phase. They will add up or constructively interference with each other if their paths are differ by multiple or integers of numbers of lambdas. Okay, delta r means their path differences. So that equals to path one minus path two, path of wave one minus path of wave two. That should equal to lambda times n, where n equals to 0, 1, 2, 3, etc. And the two waves will destructively interfere with each other if their paths are different with half lambdas. So delta r is the difference in their paths, and then equals to 2n plus 1/2. So that gives you halves of lambda. N is equal to 1, 0, 1, 2, 3. Okay, if the two sources are in phase. On the other hand, if the two sources are in the opposite phases, that means they are different by 180 degree or pi, then they interfere destructively if their paths are different by lambda times integer numbers 0, 1, 2, 3. And they interfere constructively if their wave path difference are half lambdas. Okay. So that's the other way around. All right. Now mathematically, for y1 stands for wave 1, y2 is wave 2. So y1 is a function of position and then also time t. Now y2, if it slightly differ by a phase difference of delta, so delta is small. So then y1 plus y2, you can add them up algebraically. So the result will be 2 times a cosine delta over 2 and then sine of kx minus omega t plus delta over 2. Okay, k is 2 pi over lambda and omega is 2 pi over frequency. All right, or it's 2 pi over period. Sorry, it's 2 pi times frequency or 2 pi over period. So then this is a resultant wave function. Okay. If delta equal to 0, then the two add up constructively. If delta is equal to pi or 180 degree, then they cancel out, or the interference is destructive interference. We also took out like the standing waves, which basically if you have a wave being confined in a stream, so then in that case, you can have different configurations for the waves. You can have different wavelengths and different frequencies in the stream. Okay, so if you have both ends of the stream being fixed, then the lowest frequency you could have is equal to the v, the speed of the wave divided by two times of L, and then the higher harmonicas, you can see them in the equations here. So this is the first fundamental wavelength, fundamental frequency, higher frequency, higher wavelength. Okay. If you have the string just have one end fixed, the other end open, then the equations you get are slightly different. You can find them here for the fundamental wave frequency and the higher order harmonics. On the other hand, if you have air columns, then you can create standing waves as well in the air columns. So many musical instruments are utilizing air columns. So if you have one end of air column being open, the other being fixed, then you get fundamental frequency as V over 4 divided by L, similar to the wave standing waves on one end fixed stream. And then you have higher frequency listed in this equation over here. Okay, if you have both ends of air column open, then you'll have standing waves in the air column, similar to you have standing waves on string with both ends fixed. Okay. On another note, that if you have both ends of air column closed, then you will have similar equations to the air columns with both ends open. Okay, so basically the same equations here. Okay, so we were about to take a look on this equation problem here. This one says an organ pipe open at both ends has a harmonic with a frequency of 440 Hertz. The next higher harmonic in the pipe has a frequency of 495 Hertz. Find A, the frequency of the fundamental, and B, the length of the pipe. Use speed of the sound as 340 meters per second. Okay, so your standing wave in the air column in the organ pipe is the sound wave. Okay, so sound wave in air at room temperature has the speed above 340. Okay, so let's take a look on this one here. Let me get you guys started over here. So it tells you that the both ends are open here, so then you can take a look on the equations on the previous page. It tells you that the harmonic F frequency, so we don't know F which harmonic is this, so you can call it nth harmonic. Okay, so F sub n then is equal to 440 Hertz. Okay, now it says the next harmonic is having frequency of, so next one will be n plus 1, okay, equals to 495 Hertz. Now this is the organ pipe with both ends open. So then you can for the um, frequency, nth order frequency, then will be equal to n times f1. Okay, you can check on the previous page for the equation there, with f1 equals to v divided by 2l. Okay, so this is a fundamental frequency. This is a higher harmonic frequency. Okay, nth harmonic. Okay, so it's asking you what will be the fundamental frequency and what will be the L of the organ pipe. Okay, I'll give you guys a couple of minutes. You can try to solve for this one, and then we can take a look on the solution together. Okay. All right. So let's take a look here. It says the nth harmonic is that. So we can actually apply this equation. Okay. So we are going to call it m harmonic. So that's an unknown, and then f1 is also an unknown. So you can set it up that m plus f1 is equal to 440 hertz, right? And then you can say m plus 1 times f1, because f of n sub n plus 1, that should be equal to n plus 1 times f1, right? The fundamental. So equal to 495 hertz. Okay. So you have two equations. You have two unknowns here. You can solve for the two unknowns, right? Um, So you can do substitution, or in this case, you might be just rewrite this the second equation as, so m times f1 plus f1, right, equals to 495 hertz. You can rewrite that way. So then it's easier to do this because then this is 440. So then this, the first one is 440 hertz, right? So then you can calculate f1 directly. Okay, so f1 you can calculate it. F1 then would be 495 hertz minus 440 hertz. Okay, that would be 55 hertz. Okay, so that's the fundamental frequency you are looking for part A. For part B, you're looking for the length of the pipe. Now you can also calculate what would be the M. Okay, so if this is 55, then your N equals to 8. Okay, if you are just wondering what would be the M here. Now in part B, you're looking for what will be the length of the pipe. So you have your F1 here. You have the speed 340, so you can calculate for your length. Okay, so you can set up that 55 hertz. So basically from F1 equal to the V divided by 2L equals to the V is 340 meters per second divided by 2L. Okay, so you solve for L. You can move the arrow to this side and then this guy down here. So L then is equal to 340 meters per second divided by 2 times 55 hertz. Okay. That will give you 3.09 meters as the length of the pipe. Okay. Questions you guys might have on this one? You can unmute yourself and let me know, or you can send me your question in the chat. Okay. All right. If you are clear, we can move on to the next section of the chapter. So this one is on beats. So beats are referring to the interference patterns in time rather than in space. So previously we have looked at when you have path difference, you will have interference. Now, if you have frequency difference, okay, slightly difference in frequency, then the two wave will interference as well. So let's take a look on what's the scenario here. Okay. So if you have two vary in frequency, so let's say, so we are going to ignore the space component in the argument. We are just focusing on the frequency component. So 2 pi, so omega t, 2 pi f1 t, okay? And we are going to look at this time for the wave functions as cosine instead of sine. So basically that doesn't matter. They are pretty much the same with phase shift, okay? And then the second wave function is a cosine 2 pi f2. All right, so if the two meet in space, you add them up to be your resultant wave function. So wave total y is equal to y1 plus y2. So a cosine this guy f1 and then a cosine 2 pi f2t. Okay, if the amplitudes are the same, then you can check on the geometry trigonometry identities. This is the result of two cosine function add up. Okay, two cosines add up to be the differences of the two divided by 2, and then the sum of the two divided by 2. Okay, so equal to cosine the difference of 2 times cosine of the sum of the 2 divided by 2. In that case, if f1 and f2 are very close to each other, so then this guy will be very small. Okay, and this one, f1 plus f2 divided by 2, so it'll be pretty much the same as either f1 or f2 because f1 and f2 are very close to each other. All right. So you can see, so this is original. If you call the red to be y1, then the blue will be y2. Now, when they add up, this is the resultant. You can see that the amplitudes are decreases and then increases. All right. However, there's this oscillation of, so that's referring to the cosine function, the later one here, cosine of f1 plus f2 divided by 2. Now, the oscillation or amplitude is according to this new term here of cosine, the differences of the 2 divided by 2, okay, times 2a. So that's the um, oscillation of there, okay. So overall, you'll see the amplitude varies, oscillates, and also the total oscillation of the wave is this guy, okay. So that's what you will see. All right, so the beat frequency then was simply just the difference of the two frequencies, the absolute values, okay? Absolute values of F1 minus F2, that gives you the frequency of varying in intensity. So your intensity, the as you hear, will goes down and then comes up and goes down and comes up again, okay? All right, let's take a look on one example here. This one says you have two strings are fixed at each end are identical, except that one is a little bit longer than the other. So 0.560 longer, centimeter longer, is just half centimeter. Waves on these strings propagate with speed of 34.2 meters per second. And the fundamental frequency of the shorter frequency is, of the shorter string is 212. It's asking you what beat frequency is produced if each string is vibrating with its fundamental frequency. Okay, so basically, you're given one fundamental frequency, you're looking for the other one. And you'll be taking the difference of the two. That's the beat frequency. Okay, that's part A. Part B, does the beat frequency in part A increase or decrease if the longer string is increased in length? Repeat part A, assuming that the longer string is 0.761 centimeter longer than the shorter one. Okay. All right. So you guys can also try to work on this, and then we can take a look on the solution in a little bit later. Okay. But this guy is about the fundamental frequency as well as the beat frequency. Okay, so to look for your beat frequency f sub beat, you'll be doing f1 minus f2 absolute value. Okay, it tells you, let's call this shorter one to be f2. Okay, so 212 hertz. So you need to know what's f1. Okay, first. This is the fundamental frequency of the shorter one. So you can do for the fundamental frequency, F2 should be equal to the speed divided by 2 times L2, okay? Because the strings are having both ends fixed, so that's the equation you want to use for the fundamental frequency, okay? And then for F1, will be V divided by 2 times L1, okay, in that case. It tells you that F1 is longer, that's what we assume, okay, as F2 plus the 0.560 centimeter. All right, you can just try to see if you can solve pi A, and then we'll take on the solution together after that. All right, let's take a look here. So let's draw the two streams here. This is one is longer than the other ones, and then we call this as 2. This guy is 1 here. All right. So it gives out the beat fundamental frequency for the second one. We can actually calculate what's the length of it, right? And then this is this 0.560. So we can calculate that one, and then we can calculate what's L1. So if we can calculate L1, then we can use this equation to find F1, right? So then we have F1, F2. You can calculate what your beat frequency. Okay, so it looks like the first thing to do is calculate this guy. And then after that, you can calculate what the length of this guy, and then use that length, you can calculate this. Okay, so once you have that, you can go back here. All right, so let's find L2 first. So from here, you can see L2 then will be equal to the V divided by 2 times F2. Okay, the V is given as 34.2 meters per second divided by 2 times the frequency 212, okay, hertz. And that gives you L2 as 0.08066 meters. Okay, and this one, this is in centimeter. You can convert it into meters, 0.00560. Okay, so then you can see you are having 1, 2, 3, 4, 5 decimal places. Okay, so that means you want to keep about 5 decimal places here. So 1, 2, 3, 4, 5. Okay, in that case. So then once you have that, you can calculate your L1. So L1 is equal to L2 plus the 0.00506 in meters. Okay, 0.08066 in meters plus 0.00560 in meters. That will give you 0.08626 meters. Okay, so that's your L1. Once you have your L1, you can calculate what's the frequency, the fundamental frequency of the first stream. So then F1 equals to the same speed for the for the waves in the two strings divided by 2 times of the length of the first string. So that tells you this frequency is equal to 198.2 hertz. Okay, so once you have that, you can calculate your beat frequency. So beat frequency is equal to the differences of the two absolute value minus 212 hertz. Okay, so that gives you this as 13.8 hertz for the beat frequency. All right. Okay. Now in B is asking you, let me pause for a few seconds to see if you guys have questions on part A. You can mute yourself to speak up or put your questions in the chat, okay? All right, so in B it says that's the beat frequency in part A increase or decrease if the longer string is increased in length. So if you have the length increased, one is the longer one. So if this increase, then the frequency decrease, right? If that decreases, beat frequency in this case is equal to absolute of F1 minus F2. And then we know F2 is the larger one, F1 is smaller one. So F2 minus F1, right? So if this guy decreases, then beat frequency will increase, right? So we can rationalize that this will increase, okay? If the length increases on 1, then the beat frequency will increase, okay? Now it's asking you if the difference is 0.761 in centimeter, what will be the beat frequency? So we can calculate, okay? So then we can use this, the L2 already. We can just calculate the new L1 because that's the one has length change. We'll then have the new F1, and then we can calculate the new beat frequency, okay? So then we can start from L1 will be equal to the L2 plus the difference, okay, 0.761 in centimeter. We'll convert it into meters. So previously L2 is 0.08066 meters plus this guy 0.00761 meters, okay? So then this will give you the new length for L2S. I actually didn't calculate that, but we can do that right away. So it's 1, 2, so 7, no, 7, and then 2, and then this would be 8, okay, 8. So 0 0.08, 0.08827 in that case. All right, so then F1, you can calculate what's your F1. The new F1, so we call it F1 prime. So this is L prime, V divided by 2 times L prime. So 34.2 meters per second divided by 2 times of 0.08827 meters, okay? That gives you the new frequency as 193.8 hertz, okay? So then the new beat frequency F prime will be absolute value of 193.8 minus 212 hertz. That gives you 18.2 hertz as your new beat frequency, which is greater than the 13.8 you got in part A, okay? All right, any questions you guys might have? All right, if you are clear, so let's move on to chapter 17. So this is about the basically the sounds, the physics of hearing is associated with the sound. So sound and sound waves here, okay? So sound is also a wave. So like sound wave hits your ear and then you hear it. Okay, so that's the hearing. The hearing is the perception of the sound, similar to the vision is the perception of visible light. Okay, when the sound wave is produced, it propagates in air most often. Okay, so in this case, the air molecules will vibrate back and forth in the direction the sound is propagating. If you look at the density of air, you'll see that in some positions you will have more aggregate air molecules, and then in some area you have dilute air molecules, etc. Okay, so that will be a sign function. And then if you look at the pressure, air pressure there, when the sound is propagating through the air, you'll see that as well as a sign function. Higher density and then lower or higher pressure, lower pressure, etc. Okay. And when the sound wave hits your eardrum, and then there's pressure on eardrum that trigger your nerve, and then the rest you guys know better than me how the brain reacts to the signals from the nerves. Okay. All right. Sound wave is also a wave, so then also this the quantities here are relevant: wavelength and period and frequency. Okay, and then the speed of the wave as well. So for sound, speed of sound in air, it's again this 343 meters per second at 20 degree at room temperature. Sound also is propagate in other materials as well. So like solid metals, and then waters, and then the other gases. So you will find this in this table, the speed of sound in solid or metals are much quicker than they are in airs and then or in liquid, okay, in that sense. You probably would notice that it also the speed of sound also depends on temperature. Okay, so if you have higher temperature, for example, the last two in the equation in air, if we are 20 degrees Celsius, the speed is slightly faster than the when the air is at 0 degree. Okay, and similar for fresh water, the two speed are slightly different. Um, so in the equation, the wave speed of sound wave that's proportional to square root of t, okay, divided by 273 in Kelvin. So t should be also in Kelvin, okay. The root mean square, the speed of sound in gas is related to average speed of the particle of the gas as well. So the root mean square of this gas particle is equal to this guy, which we learned before, okay. So that speed of light, speed of sound is related to this root mean square speed, okay. All right, so that's on the speed of sound. The next section here talks about the sound intensity and in sound level. Okay, so when we hear sound, that's because the sound carries energy, and then when we hear it, hits our eardrum over the area of eardrum, so that gives you the intensity. Okay, so basically you are hearing the intensity, or your eardrum experiences the intensity of the sound. Okay, when the intensity is higher, you feel the sound is larger, it's the louder, right? When the intensity is lower, you hear the sound is weaker. So intensity is defined as energy divided by the area through the given time t. Okay, so I equals to E over A over T. And because E over T is P, so then I can be rewritten as P over A. Okay. So most of the cases, the sound or the when the source gives out a wave, then it actually propagates in 3-dimensional. So it propagates out as spherical waves. Okay, so in that case, at distance r away from the source, then the area of that sound touches is equal to 4 pi r squared. So that's a spherical area. So intensity at distance r away from the source is equal to the power of the source divided by 4 pi r squared. Okay. Now our eardrums receives or react to the sound intensity not linearly. Actually, it react to it in logarithm scales. Okay, so that means the intensity levels we hear, or our perception of the levels, we call it beta, is equal to 10 decibel. That's the unit we use to describe intensity level, times logarithm of intensity divided by the I naught, which is the threshold of the sound that we can hear. Okay, the faintest sound that can be heard, that equals 10 to the minus 12 watts per meter square. Okay, so that's the intensity level, okay, that we can hear. So if the intensity, this is the decibels. Okay, so from 0 to 10, or from 10 to 20, so that's like 2 times our loudness. That's what we feel. Okay, so if the beta equal to 10, if we call that one intensity level, then the next one, or when we hear the twice as loud is 20, and then 3 times as loud is 30, 40, etc. Okay, so that's logarithm scale. So I should say the intensity of the sound doubles each increase in intensity level of 10. So this is twice. From 10 to 20 is twice. From 20 to 30 is also twice as loud. From 30 to 40, so 40 is twice as loud. Okay, etc. All right. So let's take a look on a couple of examples here. The first example is says a crying child emits sound and with an intensity of 8.0 times 10 to the negative 6 watts per meter square. Find the intensity level in decibel for the child's sound. Okay. So on this one, let's take a look on this one here. Together. So for intensity level is defined as 10 dB times log of intensity over intensity naught. I naught is equal to 10 to the negative 12 watts per meter square. So in A, you are looking for what would be this given I is equal to 8.0 times 10 to the negative 6. Okay, so we're looking for beta. Beta then equals to 10 dB. I think we can plug in the numbers here, minus 6 over 10 to the minus 12. Okay, so that will give you 69 decibel. Okay, also you might want to take note decibel as dimensionless, just like radian. Okay, part 2 is asking you the intensity level for this child and its twin, both crying with identical intensities. Okay, so when the twins are crying in the identical intensities, so then beta of the two, it should be equal to 10 dB again. Logarithm of I, in this case, I will be twice of the original I, right? Divided by I naught. So then it will be 10 dB log of 2 times 8.0 times 10 to the minus 6 over 10 to the negative 12. Okay, that will give you 72 dB. Okay, so when the intensity doubles, the intensity level does not double. Okay, it's just increased by 3 decibel. Okay, beta is plus when intensity doubles. Okay, 2 times I gives you plus 3 dB for intensity level. Okay, or in other words, we don't hear like the intensity level doubles in that case. Okay. All right, questions you guys might have? If not, that's I think that's another example here. Okay, so we'll take on this example as well. So this one says the residents of Hawaii are warned of the approach of a tsunami by sirens mounted on the top of towers. Suppose a siren produces a sound that has an intensity level of 120 decibel at a distance of 2 meters. Treating the siren as a point source of sound and ignoring reflections and absorptions, find the intensity level heard by an observer at a distance of A12, B21 meters from the siren, and see how far away can the siren be heard. So let's see. So it gives us that beta equals to 112 dB. So I'm going to say this as beta of 2 meters. Okay, it's that equal to that. And then the distance is 2 meters. So for the intensity level, it's equal to 10 dB. That's the equation. Log of I over I0, where again I0 is 10 to the negative 12 watts per meter square. Okay. So then it asks us to find beta at 12 meters. Okay. So then we'll be calculating that use this equation, right? Beta 12 should be equal to 10 dB log of I at 12 meters, right? So the question is, what's the I at 12 meters? All right. We also learned just a couple of minutes ago that intensity is equal to the power as the source divided by 4 pi r squared, right? So by given beta at 2 meters, and we can probably calculate what would be the intensity at 2 meters, right? Because this is 120, and then you can calculate that I at 2 meters. If we have I at 2 meters, we can figure out what's the power, right? If we know the power, we can well calculate what will be this guy, the I at 12 meters, right? By using the equation. Okay, so let's do that first. Let's figure out what's I2 first. I2 is equal to, no, we should use this equation. Sorry, we should use the equation to find I2. So 120 decibel equal to 10 decibel times logarithm of I at 2 meters over 10 times negative 12 watts per meter square. Okay. So the 10 dB and 120 dB will cancel out, makes it 12 on this side, right? So then that gives you log of I, this over this is equal to 12, right? So to get rid of log, you do 10 to the 12 on this side, and then 10 to this, the log of the to the power of log, okay? In that sense, you get rid of log in that case, okay? So then you will have just I at 2 meters divided by 10 to the minus 12 watts meter square, okay? So then I at 2 meters will be, multiply both sides by this, okay? So 10 to the 12 minus 10 to the minus 12, that gives you 1. So that basically tells you at 2 meters, the intensity will be 1, okay? 1 watts per meter square. Now, given that I at 2 meters should be equal to the power divided by 4 pi times 2 meters square, right, in this equation. So then you can calculate your power is equal to, so this is 2 to the 4, and then 4, 16 pi, okay, 16 pi. Yeah, this guy's 1. Sorry, I forgot to mention, we calculate that's 1 watts per meter square, okay? So this is our power at that point. Once we have power for the source, we can calculate the intensity at 12 meters, right? So intensity at 12 meters then equal to the power is the 16 pi watts per meter, or watts per meter square, over 4 pi times 12 meters squared, okay? So that will give you, I'm doing this in fraction, so this times this will be 48. No, actually this is 144 times 4, okay? So basically this will be pi and pi will cancel out. Actually, there's no pi there. 1 over 36 watts meter square, okay? So then your beta at 12 meters will be equal to 10 dB log of 1 over 36 divided by 10 to the negative 12, the I naught, okay? That equation again, that gives you, this is equal to 118 decibel, okay? So that's what you heard over there. I'm going to pause a little bit here to see if you guys have questions about this one. All right, So if not, then we'll be looking at part B here. It's asking you what would be the intensity level at 21 meters. Okay, so then part B for at 21 meters, you'll be finding intensity at 21 meters first, right? So that's the same P over 4 pi, but this time over 21 meters squared. The P we get is 16 pi from the previous part divided by 4 pi 21 meters squared. Okay, and then again, I'm expressing this in fractions here. It's 4 over 21 squared. Okay, watts per meter squared. Pi and pi cancel. This and this cancel before. Okay, so 4 over 21 squared. So then intensity level at 21 meters will be again the 10 dB log of I will be this I here. So 4 over 21 square divided by I naught. Okay, they are in the same units. That will give you 99.6 dB. All right, so basically repeating part A, what you did in part A. The last part here is asking you how far can the siren be heard? Okay, so that means at what distance. Basically, it's asking you at what distance is the intensity of the siren be the threshold of what we can hear, right? So that means you're looking for when I of certain R that is equal to 10 to the minus 12, right? That's what you're looking for. All right. So I for the intensity equation is equal to the P over 4 pi R squared, right? So if I is equal to 10 to the negative 12, we can set it up 10 to the negative 12 watts per meter squared equals to P would be the 16 pi, right? 16 pi watts per meter squared over 4 pi times R squared, and you solve for your R squared, okay? So this guy and this guy will become 4 on the top, okay? So your R will be equal to, in this case, you multiply both sides by R squared, right? R squared. And divide both sides by 10 to the negative 12, right? So divided by 10 to the negative 12. So R squared will be equal to 4 divided by 10 to the negative 12, right? All right. So then this is 4 times, yeah, this is 4 times 10 to the 12. That should be meters square. And your R, you will take square root, right, to get that. So square root of this side and then square root of that will give you your R. R is equal to 2 times 10 to the 6 meters, all right? So that's how far the siren can be heard. This number looks very big, but it's the assuming that we are very, we are kind of very, it's assuming that the, I'm sorry, there's a, this guy doesn't have, it's just watts, okay? It's not watts per meter square. So this is assuming that there's no refraction and absorption. So in reality, the air will absorb a lot of the sound, and then the refraction of the objects like opticals in between, like the mountains, etc., will also reduce the intensity a lot. So in reality, it shouldn't be this far away, okay? All right, any questions you guys have? Okay, so if you guys are clear, I'll stop here for today, okay? I'll see you guys back in lecture on Wednesday. Also, like this Wednesday is the makeup section, okay? This week we do not have new labs. If you are up to date on your lab activities, then you don't have to come for the lab. But if you have missing labs you wish to make it up on Wednesday, you are welcome to let me know, and then we can have your lab makeup. Okay, so I'll see you guys